Okay, here's part 4. I'm going to talk about section 7.5, solving initial value problems. So we actually solved one initial value problem at the very beginning of section 7.4 using the Laplace transform, but now we're going to look more in depth at that process. So we'll start off with an example. The example is y double prime minus 2y prime plus 5y equals negative 8 e to the negative t, with y of 0 equals 2 and y prime of 0 equals 12. Okay, so the first thing we're going to do, just like in that earlier example, is take the Laplace transform of both sides of our differential equation. And to make the notation simpler, I want to let capital Y of S be the Laplace transform of my solution y of t. Okay. Now, first of all, we brushed over this back in section 7.4. The main emphasis of that section was on finding inverses, not solving differential equations. So there's a technical conceptual part that we brushed over. And that is, how do I know that this very first step right here is even mathematically valid? How do I know that this is even possible? Okay, so first of all, I know that there is a solution. We have existence and uniqueness theorems. We have a solution. It is continuous because it is differentiable. So I have a continuous solution. But remember the definition of the Laplace transform. It involves an improper integral. And improper integrals can be convergent or divergent. And when they're divergent, we say the Laplace transform doesn't exist. So the first thing I would need to worry about before I even begin is, how do I know that the Laplace transform of the solution exists? And we had a theorem from before that said that if you have a function and it's piecewise continuous and has exponential growth, then the Laplace transform exists. So I have to wonder then, how do I know before I begin, before I know what the solution is, how do I know that the solution has exponential growth? If it doesn't, then everything that I'm about to do could be invalid. Okay, well, let's just, well, the main trick is, and it'll sound weird, is to worry about that later. So let's just pretend that we know that it's okay and see where this takes us. Okay, so we're assuming, really, and it's an assumption, that the solution has a Laplace transform. And given that assumption, I'm going to call that Laplace transform capital Y. Okay, now we start. All right, so what do? We take the Laplace transform of both sides. And on the right, I have the Laplace transform of negative 8 e to the negative t. Okay, so I've got the Laplace transform of y double prime minus 2 times the Laplace transform of y prime plus 5 times the Laplace transform of y is equal to negative 8. And then that Laplace transform of e to the negative t, we can read that off the table, 1 over s plus 1. And then we're going to use our rules. The rules from table 7.2 are the properties for the Laplace transform of a derivative. So for the transform of y double prime, I get s squared, and now I'm going to use my shorthand notation, capital Y of s, minus s times little y of 0, minus y prime of 0. Okay, so that's what I get for y double prime. And then I have minus 2, apply my property to y prime, and I get s times capital Y of s minus little y of 0. And then I have plus 5 times capital Y, and that equals negative 8 over s plus 1. All right, now let's expand all this. So I'm going to have s squared capital Y. Let me drop the of s because it's already getting big notationally. Now, this is an initial value problem, right? If you scroll up here, y of 0 is 2 and y prime of 0 is 12. So I have numbers that I can plug in for the little y of 0 and the little y prime of 0. Now, when you use this property in table 7.2 for script L of y double prime and L of y prime, you always get a little y of 0 or a little y prime of 0. So in order to apply this method here, we need to be looking at initial value problems that have t0 equal to 0. If t0 doesn't equal 0, then we cannot apply what we're doing here directly. We'll see what to do in that case in another example. Okay, so y of 0 is 2, so this gives me minus 2s. Y prime of 0 in this problem is 12, so I have minus 12. Then I have minus 2s capital Y plus 2 times y of 0, so plus 4. And then I have plus 5y, and that equals negative 8 over s plus 1. Now let's solve this thing for capital Y. So let's collect all the capital Y terms, and I have s squared minus 2s plus 5 times capital Y is equal to, and we'll put everything on the other side. So I have negative 8 over s plus 1 plus 2s plus 12 minus 4. So plus 8. Let's take that right-hand side and put everything over a common denominator. So I have minus 8 plus 2s plus 8 times s plus 1 over s plus 1. And then if we multiply and out and simplify the numerator, I get 2s squared plus 10s over s plus 1. And then finally, solving for y, I get y equals 2s squared plus 10s over s plus 1 times s squared minus 2s plus 5. Then to get little y, which is the solution I'm looking for, I need to do the inverse Laplace transform. Little y is L inverse of capital Y, and to get that, we would use partial fractions. Of course, we already did this exact one in the last section, so we don't have to do all that work. We can just write it out. So the inverse is negative e to the negative t plus 3 e to the t cosine 2t plus 4 e to the t sine of 2t. Okay, and I feel like I'm done, but let's go back to the very beginning when I said, how do I even know that my very first step was valid? None of this is valid if the solution doesn't have a Laplace transform. If the solution doesn't have a Laplace transform, then everything that I just did is nonsense. Yeah, because I'm doing math on something that doesn't exist. Okay, well, there's an easy fix for that. Instead of trying to rely on all the work that I just did, I could consider all the work that I just did as a suggestion. It's pointing me to this candidate solution, this potential solution. And now I just have to check that this is the solution to the given initial value problem. And we know from way back in the beginning of the semester that it's much easier to check that something's a solution than it is to find a solution in the first place. So really what we should be doing to be completely mathematically pure and make sure we've covered all of our bases, we really should check that this is the solution. We're not going to do that, though. And you have my permission to take it for granted when you see a problem of this type given to you in the homework or on a test that unless it's otherwise stated, you can assume that the the solution has exponential growth and has a Laplace transform, and so that all the steps that you do in this method are valid. But I wanted to point out that little subtlety because it's there. It's a mathematical reality, and you should be aware of it. But in practice in this class, when you're doing problems, you can assume that the solutions have Laplace transforms, and everything that you're doing is legitimate. You don't have to check at the end as a separate final step that this thing really solves the equation. Okay, let's look at another example then. Y double prime plus 4y prime minus 5y equals t e to the t. We're going to have y of 0 equals 1, y prime of 0 equals 0. All right, take the Laplace transform of both sides. So I have L of y double prime plus 4y prime minus 5y is equal to the Laplace transform of t e to the t. All right, so this one, for L of y double prime, I get s squared y minus sy of 0 minus y prime of 0. Okay, then I get plus 4. Then I apply the rule for y prime. So I get s capital Y minus y of 0. And then I have minus 5 times capital Y. And that's equal to the Laplace transform of t e to the t. Again, we're going to read that off of our table. Laplace transform of t is 1 over s squared, and because of the e to the t there, it's going to be 1 over s minus 1 squared. In this problem, y of 0, y of 0 is 1, y prime of 0 is 0. Okay, so simplifying that then, I have s squared capital Y minus s plus 4s capital Y minus 4 minus 5 capital Y is equal to 1 over s minus 1 squared. Gathering all the y's together, I have s squared plus 4s minus 5 times y is equal to 1 over s minus 1 squared plus s plus 4. Put that over a common denominator. I get 1 plus s plus 4 times s minus 1 squared. Over s minus 1 squared. And then multiplying that one out and collecting like terms, you're going to end up getting s cubed plus 2s squared minus 7s plus 5 over s minus 1 squared. All right, finally we're going to solve for y. So I have y of s is equal to, here's my numerator, s cubed plus 2s squared minus 7s plus 5. Okay, I've got that s minus 1 squared, and then I want to divide by s squared plus 4s plus 5. While I'm dividing, I might as well factor, so that factors as s plus 5 times s minus 1. And we can put those two together, the s minus 1 squared and the s minus 1. Let's do that. So I end up with s minus 1 cubed times s plus 5. And now I want to do a partial fractions decomposition. I check that this is a proper rational function. The degree of the numerator is 3. The degree of the denominator is 4, so it is proper. And I can now break it down. I have two linear factors. I have 4 linear factors. They're all linear, so I'm going to have 4 fractions. They're all linear, so they're all just going to have constants on top. The first one appears to the power of 3 So I'm going to get an s minus 1, s minus 1 squared, and s minus 1 cubed. The last one is just by itself, so I have an s plus 5. Okay. Multiply both sides there by the denominator. We have s cubed plus 2s squared minus 7s plus 5 is equal to a times s minus 1 squared times s plus 5 plus b times s minus 1 times s plus 5 plus c times s plus 5 plus d times s minus 1 cubed. Okay. Now for this one, you can do it in use the method where you multiply everything on the right-hand side out, collect like terms, equate coefficients. You have 4 linear equations and 4 unknowns. Solve them to get the values of the constants. You could try plugging in key values like s equals 1 and s equals negative 5 to figure out some of those coefficients. That's not going to be that effective. You will, because you have 2 key values to plug in, but you have 4 coefficients to determine. So it's not going to get you all the way there. You're still going to have to do a lot of algebra. I don't think it's worth it. We did in the last video a lot of that, so I'm not going to go through all of that algebra in the video here. I'm just going to skip that. I'll tell you what the what values you end up getting. You end up getting, if you plug in s equals 1, you'll end up getting c equals a sixth. Plugging in s equals negative 5, you're going to end up getting d equals 35 over 216. And then you can do other values or other methods, and you're going to end up with, what do we get here? A equals 181 over 216, and b equals negative 1 over 36. Okay, so putting that back into our equation for capital Y, we end up with capital Y of s is equal to 181 over 216 times 1 over s minus 1 minus 1 over 36 times 1 over s minus 1 squared plus 1/6 times 1 over s minus 1 cubed plus 35 over 216 times 1 over s plus 5. So our solution, and again, we're just taking it as our practical assumption in this course that the solution has a Laplace transform. Everything we've done is correct. So we are going to take the inverse Laplace transform and not bother to check that this is a solution. Just say, okay, this is the solution. All right. And we can read these Laplace transforms, inverse Laplace transforms, right off of our table. So the inverse of 1 over s minus 1 is e to the t. Then I've got the inverse here of 1 over s minus 1 squared is t e to the t. Okay. And then the inverse of 1 over, well, if you read it off the table, you need to say that it's the inverse of 2 over s minus 1 cubed. And that inverse would be t squared, e to the t. But if I'm going to make that a 2, I need to make that a 12. And I've made that change because 2 over s minus 1 cubed, that's what you can read right off of the table. And that's how I think about these things. It's an easy way to match it up to what you're looking at on the table. So this is going to be plus 1/12 t squared e to the t. And then the last term, got my constant, 35 over 216, and e to the negative 5t. That's our solution. Okay. I think we need to do a part 5. Now we're on 20 minutes for this video. Hopefully part 5 will be our last part, and we'll be done with this section, and that's going to be it for the week. So I'll stop now, and we'll see you in part 5.